Okay, thanks, Martin. First, I would like to thank all the organizers for organizing this really nice meeting and inviting me to give this talk. Okay, so I'll be talking about a really simple problem. I mean, in some sense, it's it looks like quite trivial, right? Just ideal gas expanding. But there are sort of interesting questions, and so this is work done with a lot of people during this last 3 years during COVID. So this Shubhadeep Chakraborty was a postdoc at ICTS. He's now in Nuremberg in Germany, and Junaid and Saurav are two of my PhD students at ICTS. Manas Anupam is here, and Manas, their colleagues at ICTS, and Shelley Goldstein, Joel Lebowitz, and David Hughes. Okay, so this is the basic question that everyone knows about and has thought about, I'm sure. Macroscopic irreversibility from microscopic reversible laws, how do you understand this? So you can see here what exactly we mean. I mean, this is what we observe in nature. Things so this is a drop of ink that is spreading in water. You don't see the reverse motion, even though that satisfies the laws of microscopic laws of physics. Okay, so basically the point is that the observed macroscopic behavior of physical systems shows irreversible behavior. And what we know is that the second law provides an arrow of time and sort of quantifies irreversibility through the concept of an entropy function, which increases with time. Question that we always ask is, how does one reconcile reversible Newtonian dynamics with irreversible macroscopic behavior? Okay, so I mean, this is something that Boltzmann had thought about a long time back, and it's really nice that we are in this city where Boltzmann thought about these questions. So he had a very precise answer actually to this question. So what he in particular pointed out that the observed irreversibility is the typical macroscopic behavior given appropriate initial conditions that becomes a certainty when the degrees of freedom is large. Okay, so this is one important that you need, initial conditions that are the typical initial conditions, not very special initial conditions, and a large number of degrees of freedom. So the second point is that Boltzmann also provided a very clear prescription for the construction of an entropy function that is defined actually for a single microstate of a system. So normally we are used to thinking of entropy as like it's computed over an ensemble and so on. But there's a simple prescription to compute it for a single microstate. And this Boltzmann had already given this prescription. So this entropy function is defined for a system both in or out of equilibrium, and it is equal to it equals the thermodynamic entropy, equilibrium entropy for a system in equilibrium. Okay, so this is basically what I'll try to explain. And so this, this question of the arrow of time, this is a very nice article by Joel Lebowitz, which gives a sort of qualitative discussion of this problem. This is the paper which sort of makes this very clear, and all these discussions very clear. So this is a paper that I would very strongly recommend for if you want to understand this talk. And then there are these other papers which have also discussed this question. These last three are in the context of quantum systems. Yeah. Or yeah, so you can define that's what I'll explain. Okay, so what the system that I'll talk about is a one-dimensional gas of non-interacting particles, and initially, so you can just think of free expansion in a box. So initially, all the gas is confined to one half, and then they just you open the partition and it expands. Now, if you think a little bit about it, it's clear that this is what, even if it's a non-interacting gas, this is what you'll see. It spreads and becomes uniform, and it's unlikely that it will go back to this configuration, right? Okay, so Okay, so this is the initial condition. We choose just one microstate, which is chosen from a thermal distribution, let's say, but it's just one single microstate. We'll also look at other initial conditions and try to point out the role of initial conditions. And the particles are just following Newton's equation. In this case, they're just moving at constant speed and colliding with the walls at the ends. Right? That's dynamics. They pass through each other and so on. So in this case, it's clear that we expect irreversibility. How do we quantify this through an entropy function defined for a single microstate? Okay, so I'll now introduce these concepts of microstates and macrostates. So microstate is, of course, the positions and momentum of all the particles in a box. And then the dynamics is given by some Hamiltonian h of x. And a macrostate is like, it's a coarse-grained description of a system. So simple example is like in this room, we have gas. And if I just look at what is the number of particles on the left half, this half of the room, that's a macro variable. So for example, out here, if I just count the number of particles on this half, that's a macro variable, okay. And so the value of the macro variable, let's say the number of particles in the left half, is clearly a function of the microstate, right? That is clear. And also what is clear is that there are many microstates which correspond to the same the same value of the macro variable. So if I specify the number of particles on this left half, I can obviously find a large number of microstates which correspond to this macrostate. And so I'll call this gamma m as the number of such microstates. And then I can define entropy, Boltzmann's entropy, just as kp log gamma m, right? So this is the basic idea. Okay, so let me make it, let me give examples and make it more clear. So let's say there's a box and there are these particles, and I just, for the moment, I just look at the positions of the particles. So there are 16 particles, and now I can consider a microstate means I give the precise positions of all these particles. Now, a particular macrostate could be like I divide the box into cells of sort of large cells. And in this case, there are 7 cells, and I just count the number of particles in each cell. Okay, so this basically gives me the density profile in the box. So these macro variables, so this is what I will call a macro variables, and if I specify the numbers, it specifies the macrostate. Okay, so now I can ask, given a particular value of macrostate, how many microstates are there? And in this case, of course, this is it just becomes like in each of this, like I can ask, given this some number of particles, what is the volume in phase space occupied by this configuration? And then it's clear that the number of the volume in phase space corresponding to this specification of the macrostate, which is just the number of particles in each of the cells, is given by this, right? This is something that people have seen. And therefore, now I can associate an entropy with the microstate. Okay, so there's just log of this, and this is what one gets. So rho is like the density in each box, and I sum over all the cells, and this is the entropy. So I hope, Martin, this is clear, right? This is how I define entropy for a, so given a microstate, I can associate with it a with the entropy, provided I first identify like my coarse-graining, like what is the level at which I can look at this? What is my knowledge about the system? It's not unique. It depends on my what I am able to observe, right? So in this case, if I'm just looking at the density, this is what I would, this is the entropy I would associate. But I can look at various quantities and I'll get a different entropy. Yeah, maybe you should include it. Okay, so now the basic idea of like why entropy increases is the following. Like if I look at the entire phase space, each macrostate, the value, if I specify the macrostate, that will correspond to some volume of this phase space, right? So now it just happens that what I call the equilibrium macrostate. So in this, I mean, then what is the equilibrium? If I'm specifying density, of course, the uniform density is what I will expect to be the equilibrium macrostate. If I count the number of configurations for that choice, that will be fill almost the entire phase space. Okay, so that has the most largest entropy, and all other macrostates have like much smaller volumes. Okay, so this is kind of partition of the entire phase space if I specify value of the macrostates. So typically, if I start from some, let's say, this initial condition where all the gas is in this half, then it might be somewhere here, and then it will move. As the point evolves in phase space, it goes through states of higher entropy. Okay, so that's why we expect that entropy should increase, and eventually it reaches the equilibrium volume. Yeah. Sorry? Yeah. Right here, yeah. So my the macro variables, it's I specify it right at the beginning, like whatever it is. It could be 2 boxes, but I fix it for all, once and for all, and then I just look at how it evolves. Okay, so this is, again, let me just summarize the basic idea of Boltzmann. Like given a microstate, I do some coarse-grained, my observations are coarse-grained, and I define a macrostate. This is a function of the microstate. And then I count the number of microstates corresponding to this macrostate, and that gives me this volume in phase space. And then I define entropy, which for a single microstate. Okay, so now we'll sort of look at 2 natural choices of macrostates and see, yeah. But I associate it with a micro. No, I'm associating it with a microstate because I want to see, like, given an initial condition, it's one microstate, right? And I want to see how the entropy evolves. So I don't want to, right? But I have to, of course, define my level of coarse-graining, which defines the macrostate. Exactly, right, yeah. Uh, I mean, okay, I don't, okay, I don't know exactly, but I mean, what he defined was like so he looked at the h, like the h function h, right, which is like an example of a coarse-grained variable. So, I mean, he had the idea, but I don't know like how exactly he understood it. Okay, so the 2 choices of macro variables that we look at are, so in this particular context of a gas, one is this the single particle distribution. So this is the object. So basically, okay, maybe I have it in my next slide. Okay, so this is, I mean, this is what actually occurs in the H theorem, right? So this is just a single particle phase space distribution. And then the other choice that we'll talk about are the usual hydrodynamic fields that we use in the hydrodynamic description. So in this case, I mean, of course, this is an integrable model with large number of conserved quantities. But supposing we just look at the 3 conserved quantities corresponding to density, momentum, and energy. Okay, so so what we know is just the profiles of these 3 quantities, and we ignore all the other microscopic details. Okay, so these are the 2 macro variables that we look at and ask how does the entropy associated with these variables change as we during free expansion. Okay, so okay, so to be more precise, the way it's the first macro variable is defined is I just look at single particle phase space, and then of course each particle will belong to some point in this phase space, right? So then I just count, so for given microscopic configuration, I just count how many particles are there in each of these boxes. And I define this, sorry, so, okay, this n should not be there. Okay, so it's a mistake. So it's just the number of particles divided by the phase space volume of, so delta mu is just the volume of each of these cells. So that's just delta x times delta v. So it's the density of particles in phase space. Single particle phase space. So using this exactly the same argument that I just gave for the like to how to compute entropy given specification of numbers in each cell, one would just get this formula for the entropy, right? So, so again, note that this is defined for a single microstate. There's no notion of ensemble or anything. It's just, I just take a microstate, count the number of particles in each cell, construct this object, and then this is, gives me my the entropy. Okay. So now, how does this quantity evolve under this situation where I have all the particles like this, and then they evolve in time? So the dynamics is just particles move with constant speed in between wall collisions. Okay, so now I show in how this in this single particle phase space how the system evolves. So this is what it does. I mean, so initially all the particles. So this is velocity and this is space. So this is so we take the in velocity it's Maxwell distributed, and in space it's uniform between 0 to let's say. So this is a box of size 4, and the particles are between here. Okay. So here there are some 10 to the 7 particles. It is easy to do because it's all non-interacting. So you just you know the exact solution, and then you just see how it evolves in time. Okay, so this is what it happens after time 4. It looks like this, and so this temperature is around 1. This is 4, and this is 8, and so on. So what you see is that in this phase space, you see a lot of structures developing. And now using the prescription I just mentioned, you can compute this entropy. And what you find is that, okay, so so these plots are this entropy as a function of time for different levels of coarse-graining. Okay, so this delta V is, so I had this cells of, so there's a delta V and delta X. So if I change delta X, this entropy curve doesn't change much. And in fact, it converges after some time. But if I change this delta V, I did get different rates of growth of entropy. Okay, so this is for delta V equal to 0.5, and this is for 0.25, and so on. Okay, so as I make it delta V smaller and smaller, I see that somehow the entropy growth rate decreases, and what one expects is that in the limit delta V going to 0, it should really, yeah. Right, yeah, yeah, yeah. So this is without interactions. That's true, right, yeah. Yeah, so I'll also talk of an interacting gas afterwards, but still without potential energy. Right, yeah, yeah, no, that's true, yeah. So if, I mean, in this case, it's a good definition of entropy, but it may not be always a, okay, so, the main points are, one is that we see that the rate of growth of entropy decreases as we decrease delta V. The second point is that it eventually there's a change in entropy which is just log 2, and then you also see this sort of, it goes to the almost the maximum value, and but then oscillates a bit. Okay, so so I'll try to explain some of these features. Okay, so yeah, that's exactly what I'll show. I mean, so there's a time scale which I'll just explain now. Okay, so I mean, so in this plot, what I show is that this is the velocity distribution at different cross sections. Okay, so at time 0, I mean, there's no gas out here, and out here it's a Maxwell distribution. Then at if I look at some time like 8, what I find is that it's no longer Maxwell anywhere. But again, at time 16, which is out here, it's a sort of Maxwell distribution everywhere. Okay, and then this keeps happening. Like I can see that at certain times, which corresponds to the maximum of this entropy, the system sort of becomes very close to a Maxwell distribution, and then it again goes back to some non-Maxwellian behavior. Okay, so there are these oscillations, and we observe that this period is 2L. L is the length, 2L divided by delta V. Delta V is the like the coarse-graining scale. Okay, so now why does this come 2L by delta V? So this can be understood by just if I, yeah. Sorry? It's some large number. So in this case, it's 10 to the 7 particles, but yeah. I mean, after some time, things converge and it doesn't change. Okay, so this can be, this 2L by delta V can be understood, I mean, basically by just looking at, let's say, one single cell of, let's say, of size something, 0.5 here, and this is delta X is 0.25. How does it evolve in time? So, I mean, of course, this is typically start traveling with speed around 1. Okay, so let's say after time 4, I mean, the particle here would go a distance of 2. So this stretches to something like this. And then this stretches to something like this. But after time 2L by delta V, I mean, what you'll find is that it winds around exactly twice. Okay, so 2L by delta V, because if you have two particles separated by delta V, then what's the time taken to sort of, again, return to the same cell? Okay, so initially they kind of separate as you go, but after some time, because it's a box, I mean, they will again be together. Okay, so if you ask what is the time, that's just 2L by delta V. So at this time periods, you keep developing, like you wind around exactly integer number of times. But if you look at intermediate times, it's like it hasn't wound around completely. So therefore, I mean, at these times, it's clear that essentially you have a log2 increase in entropy. Yeah. Sorry, say. Right, yeah. If it's not Maxwell, no, you'd still get these oscillations. I mean, yeah, so I'll show some other initial conditions where it's not Maxwell. But I mean, for example, this is it's not, I mean, here we take a distribution where it's uniform here, and it's, so it's a uniform distribution actually. So even in this case, you'll get the same oscillations. But yeah, so the basic point is that with time you develop these structures, and that's why if you if you take finer delta V, you'll see these structures, and that leads to decrease in entropy, right? Because you have more information about the system. Okay, so so the main observations are, for any coarse-graining, the final change in entropy is always log2. I mean, as the coarse-graining box size is decreased, the entropy growth rate decreases. And in fact, if you take the limit where this delta goes to 0, but first after you take n going to infinite limit, because you always need some particles in the cells, then you can show that this function satisfies equation like this. So it's clear that if you construct f log f, this does not evolve in time, right? This, I mean, this will dsdt is 0 for this if f satisfies this equation. So okay, so this is I mean, how you understand that why delta v going to 0, there's no entropy growth. But the point is that if you, at any finite coarse-graining, you always see this entropy change of log 2. Okay, so this, so like Andre said, that you can scale this data and they collapse, and we can, we have a formula for this curve, just based on what I described qualitatively. Okay, so okay, so now I'll come to the other definition of the macrostate, which is just looking at the hydrodynamic fields, density, momentum, and energy. So again, we take the cell and just construct cells of size L and ask how many particles, how much momentum and energy is there in each cell, and then construct the entropy. So in this case, so we have to again find the volume in phase space for this particular specification. And in this case, basically, you can just use, given these numbers, you can always compute the entropy associated with this cell, right? So it's just the equilibrium entropy. So this system is not really in local equilibrium, but as far as the counting is concerned, you can just use the equilibrium entropy. So the entropy of this entire thing is just sum of entropies of each of these cells, given that you know each of these numbers. Okay, so these numbers, you just, given a microstate, you can compute these numbers, and then you just use the entropy formula. And this is just the ideal gas entropy that we get from equilibrium physics. Okay, so in this case, if you look at how the fields evolve, I mean, so this is with 10 to the power 7 particles, they have some smooth evolution. And eventually, you'll find all the three fields go to constant density, the velocity goes to 0, and the energy goes to some constant value. So in this sense, I mean, even though it's a non-interacting system, if you are looking at these observables, the system does equilibrate. Okay, so this is, I just want to show that if, I mean, the large number is important. If you take a small number of particles, you'll see, like if you compute this entropy, you'll see a lot of oscillations. But as you go to large numbers, you'll just see a completely smooth profile. Okay, and in this case, if you again compute the entropy, you find that it behaves very differently from the other entropy. In this case, it's completely monotonic, and it converges as you decrease this coarse-graining length scale. So yeah, so this is monotonic and has no oscillations. Okay, any questions? Everything fails. No, like Chris was saying, if I had like attractive interactions, for example, or any potential interactions, then if I use f log f, I mean, that's not a good choice of entropy. And observables, no, I mean, given my observables, of course, the definition of entropy is unique. Right? Of course, the choice of observables is important. But I mean, I would imagine that no, like in this case, the hydrodynamic fields really don't close, right? But you still get, I mean, these three fields don't close. Because it's an integral system, it has, I mean, it, right? But it still works, I mean. Yeah, I think one can find example. Right, yeah. Yeah, right now, I mean, I can't think of a simple. Right, yeah. Yeah, I mean, okay, so of course I explained why it happens, right? And maybe the next example that I'll talk about, I mean, it's something which you'll be happy. Okay, so before I go to the next example, I just talk of some other initial conditions. So it's a very, let's say you just start with the initial condition where it's still in one half, but every particle just alternates in velocity. Okay, so this is, I mean, something which obviously won't, won't equilibrate. And if you compute, you'll just find that it periodically just returns to its same state. And there's no second law, right? I mean, so you don't see a change in entropy. But now if you take this and if you perturb it a small bit, like if for each velocity it's not plus minus 1, but you add epsilon to the velocities, then immediately you see it changes again by like it increases and saturates. So you again get back irreversibility. So except for very special choice of initial conditions, most initial conditions will give rise to change, increase in entropy. Okay, so this is, maybe I already talked about it. So, I mean, so the basic idea is that the equilibrium macrostate occupies most of phase space, and what we for non-equilibrium initial conditions, you start from outside this macrospace, and then you keep evolving to higher partitions with higher entropy. Okay, so now I'll talk about interacting system. So this is I mean, it's the same system, like there are these point particles, but now they undergo collisions, so they move. So these are point particles which move freely between collisions, and then the collisions conserve momentum and energy. Okay, so and if they're equal mass yeah. Yeah, that would be a very atypical initial condition. Yeah, but for a little while. I mean, right, yeah, it would go, but then, I mean, so it would go down to the same state, and then, but it would again then increase. I mean, so this is, of course, exactly what Zarmalow's, I mean, point was, like if you reverse trajectories, I mean, but I mean, but it's an extremely special initial condition. And the probability of that, it still sits here, but you can see that, I mean, this is a huge volume, and the probability of such this configuration is extremely low. Right, yeah. No, so that initial condition, of course, it still looks like uniform, but in terms of dynamics, it's very special. But it's the states are extremely low probability. Yeah, so, but see, for example, the two macrostates that I talked about, I mean, both of them will, I mean, there will be some, they will differ in a very small region, but almost they're like the same year. Now, I don't know if like, there's some choices of macro variables which, but if they're, I think if they're reasonable macro variables, like in terms of observations, they should still behave more or less, I mean, the same way. Okay, so so this is the model. I mean, point particles, and okay, and then their masses alternate. Okay, so it's M1, M2, M1, M2. The reason is if they're all equal masses, then it becomes like almost like a non-interacting system, because then collisions just exchange velocities. So it's effectively non-interacting. So you need to make their masses alternate between, let's say, M1, M2, M1, M2. Now, the good thing is that this is a system which has a very good ergodicity and mixing properties. And it thermalizes very fast and so on. And also its equilibrium equilibrium property is just still ideal gas. Okay, still an ideal gas, but has good equilibration properties. So in this case, if I do the same experiment, and here you see something completely different. So I mean, so this gas is now expanding, and so at some point it hits the wall, and then you see some here a lot of activity, and then eventually it's going to thermalize completely. Okay, so here you don't see this fine structures developing, and so we expect that we shouldn't see all those oscillations and strange behavior that we saw for the equal mass case. Okay, so here if you will have all those, like, so if you look at the profiles, I mean, so this is, let's say, the density profile. Initially, I mean, initially, if you look at short times before it hits the wall, then it's evolves just through the Euler equations. Okay, and it's right, yeah. So after reflection, it's completely chaotic, and that's when actually all the entropy production takes place. Okay, and in this case, if you look at these two entropies, I mean, they match perfectly. Okay, so both SF and SU, they just sit on top of each other after you do sufficient coarse-graining. Like if you take L sufficiently small, the coarse-graining length. Okay, so in this case, both macrostates lead to the same entropy. And this can be understood just by from the fact, so what was different in the previous case is that there's no local thermal equilibrium, but in this case there's local equilibrium, and then one can easily show that both entropy should be pretty much identical. Okay, and also it increases completely monotonically with time, and this change is always log 2. Okay, so in this limit, when n going to infinity, delta going to 0, for the interacting gas, this single particle distribution now satisfies this Boltzmann equation, where this is the collision term. And in this case, unlike the equal mass case where this was absent, now we know that even in this limit of delta V going to 0, this quantity will evolve. And this is essentially, I mean, Boltzmann's H function. Okay, so except for the negative sign. Okay, and for the other macrostate, the evolution is given basically by Navier-Stokes equations. And here again, I mean, this collision term will generate dissipative terms. And while at the Euler level, we have no entropy production. I mean, because of this, we get entropy production. Yeah. Sorry? Oh, right. Okay. Yeah. Thanks. Okay, so I just want to maybe point a few things here. So if I look at the time scales here, I mean, so this is the, so initially we see some very slow entropy growth. And this is the time at which, before the gas hits the wall. Okay, so this is, so if you look at this evolution, I mean, initially this is the profile, and then this spreads slowly, and at some time it hits this other wall. And during this initial evolution, the entropy production is very less, and it's mostly because of collisions with this wall. But after it hits to the wall, then there's a lot of activity, and that's when you get significant of entropy production. Okay, so finally I'll talk about some extensions to the quantum case. So in the quantum case, one can again consider ideal gas, and there we are now looking at the evolution of a typical, again it should always be typical many-body wave function, let's say, which is chosen from a thermal distribution at some specified temperature and chemical potential, and where we put all the particles in the left half. So in this case, again, we consider the same two macrostates that we studied in the classical case. And in this case, quantum Boltzmann entropy basically counts the number of independent states corresponding to a specified a macrostate. And one can pretty much carry through the formalism. So one sort of subtle issue is constructing the analog of this single particle distribution. So in the quantum case, so in this case, I mean, natural choice would be the Wigner distribution function, but this is not positive definite. So yeah, a pure state, right? Yeah. No, so let's say, I mean, we just consider like one state that's chosen from this possible, like e to the power minus b, let's say the canonical distribution or the grand canonical distribution. We just take one state chosen from that probability distribution. Right, yeah. So, so what we find is that if you take the Wigner function, it's not positive definite. But if you do a particular coarse-graining on a scale of h bar, then you can construct a positive function. This is positive, and in fact, it has a simple physical interpretation of in terms of occupancy of single particle states which are localized both in space and momentum. Okay, so using this construction, we can we have analog of this classical single particle distribution function, and we see that it shows the same kind of evolution in of the momentum. Okay, so here are, in this case, there are some also strange things like in this case, if you take this gas, you'll find that after this time, it exactly comes back to the same state. Okay, so so then how do you get thermalization? But what we find is that there's a time scale of order L during which you'll see that, for example, the density profile becomes uniform. And then on a much larger time scale of L square, it again, you see this recurrence, okay? So between recurrence and equilibration, there's a long gap. Of course, if it's an interacting system, you expect that this should be of order maybe exponential L before you see recurrence. But here it's a much shorter time scale because it's a non-interacting system. Okay, so in this case, for fermions, we find that the entropy change is not log 2, but it's between log 2 and 2 log 2 for fermions, and for bosons, it's less than log 2. Okay, so this is some stuff we are still writing down, and I'm just sort of presenting it in case I'll be happy to discuss this if anyone is interested. Okay, so so basically, I gave a demonstration of increase of Boltzmann's entropy during free expansion of an ideal gas. Boltzmann's entropy, we defined it for two choices of macro variables, and both demonstrate thermalization in with the final change in entropy, which is log 2 per particle. So I put thermalization in quotes is because if you look closely, I mean, it's not really in equilibrium, right? Because it's a completely non-interacting system. But if you are looking at particular observables, then you see that it thermalizes. So one point that we want to make is that these notions of ergodicity, chaos, and non-integrity are not so relevant for observing irreversibility and entropy increase. Typicality of initial conditions and large numbers and coarse-graining are the important factors. So for the interacting gas, we found that these two entropies, you get exactly the same dependence. Okay, so these are some references. Thank you.